Okay. Excellent. Good morning, everybody. I hope everyone's having a wonderful day. So today I'm going to be picking up from where I left off last time. I introduced you heap sort. So remember, this is a big theta n log n time algorithm that uses a constant amount of additional space. So that's really nice. So I took the idea of our priority queue, and I showed you that there's actually a close relationship priority queues have with sorting algorithms. And depending on how you implement the priority queue, it actually varies what the sorting algorithm basically looks like when I remove all the bits and pieces of the priority queue. In this case, if you use a binary heap, if you use a priority queue, you end up getting effectively heap sort. And then I showed you a couple of small little tweaks you can make using heapify and the way I store the elements in the array so that I can get rid of that additional space that I was using for my setup. So I wanted to do an example with you, just going through the whole process of heap sort. So I just wanted to start off with an arbitrary array, and I want to walk you through how I'm going to do heap sort on using my heap-based approach. Now remember, in heap sort, instead of using a min heap, I use a max heap. Now it's worth noting that if I used a min heap, the elements would come to me in reverse order. If I'm assuming they're going to be smallest to largest, they'll be largest to smallest. If you find yourself curious about that and like, oh damn, why do you need a max heap as opposed to a min heap? It's because they'll come in reverse otherwise. But so if you need it that way, that's just a fun little tidbit for you. I want to walk through this. So remember, I've got to first apply heapify to make this array into a max heap. Now remember, the only things that change from a min heap to a max heap is all my key comparisons, they're all flipped. So wherever I had a less than, it's now a greater than. If it's a less than or equal, it's a greater than or equal. Otherwise, all the algorithms are the exact same that I showed you the other day. So remember, it's about the middle. Remember, it's the floor of n minus 2 over 2. If I have n elements, in this case I have 6 elements. And that'll get me to right here. So my start index will be right here. And what I'm going to do is I'm going to incorporate each one of these. Then I'm going to perform a bubbling process to get into the right spot. I'm going to need to do a little bit of the bubbly, okay? So let's see here. I'm going to have, let's see. So I'm going to incorporate 7 into this. Now remember, it's supposed to be a max heap. So remember, what's going to be up here or at any root of a heap was always going to end up being the largest or maximal element of that heap. So for example, when I incorporate 7 into this, you'll notice that I'm not going to move 7 down here and perform a swap like I would with a min heap. So I didn't have to do anything interesting here because I didn't have to bubble down. So now I proceed over here. So now I'm going to incorporate this 2. So I decremented the start index by 1. And now I'm going to put in 2. So now when I put 2 right here, you'll notice that this, if I look at the heap, when I just only consider this right here, notice that this isn't a max heap. So recall, what I need to do is I need to take, so remember, in a min heap, I selected the smaller of my 2 children when I had 2 children. Here, I picked the larger of the 2 children. So if I have 3 and 4, I'm going to swap in my bubble down process with the 4 and the 2. So I end up swapping these two, the 2 and the 4. So now 2 goes here, 4 goes there. So 4 is here now, and 2's right there. So remember, just think in everything I did before. Just remember, whenever it's less than, now it's greater than. So far, are we doing okay? So I haven't really done anything too clever yet. Remember, it's just a max heap, not a min heap this time. And now I'm going to incorporate 8. Now I'm going to incorporate 8. So let's put 8 in. Now, do I need to do anything at this stage? Can somebody tell me, is this a max heap? Very good, very good. Very good. It is. Perfect. Everybody's on the ball. like I said, perfect. So now we're done that first part where we had to apply heapify. Now I'm going to do this second part I described, where I'm going to start at the back and I'm going to work my way to the front, and I'm going to perform remove min, well, what a town amounts to a remove min operation. Instead, what I'm going to do is I'm going to swap each one of my elements with the first position. And as I do this, I'm going to actually create more space towards the back of this array. And that's going to be where I'm going to store my partially sorted array as I do this. So the first thing I would do is I would take this and I do, let's see. So I start off with 8 here. So I'm going to swap. I'm going to put 8 over here. So I'm going to put 8 over here. So now remember, 8 is a part of the partially sorted portion of this heap. So as far as we're concerned, it's gone from the heap. It's gone from the heap. And then what I do is I put the 1 here. However, now notice that there's now a problem. Now I have to use my bubble down process. And now I have to swap 1 and 7, because remember, 7 is the larger of these two. So I swap them. And now I have 7 right here, and 1 will go right there. Are we okay with this so far? So remember, the only part that we care about now is just this, and when we're done, this whole array will be sorted. So now the next one I'm going to consider. Yes? Oh, thank you. Thank you. I actually didn't update this yet. There we go. There we go. 7, 4, 1, 3, 3, 2. There we go. Yeah, thank you for pointing that out. I was about to look at this and like, oh, well, yeah, thank you so much. This is why I like doing it with everybody. That way we could do this together. I really appreciate that. So let's do the next one. So I'm going to now swap 2 with 7. Because remember, this is, in fact, the next largest element. So I'm going to swap 2 and 7. 2 and 7. So now remember, I'm going to boot 7 out of my heap. 2 is going to go up here. So now 2 is gone. I know for some people, when I see rubbing my finger on this whiteboard, they're like, oh, Dan, don't do that. Please don't. But let's, anyway, so now look at this. This isn't technically a max heap anymore. So I just picked the larger of my 2 children. And I performed the swap. So now I have to swap 2 and 4, because 4 is the larger of my 2 children. Am I done yet? Somebody tell me. Am I done yet? Is this a max heap? No, exactly. So I'm going to have to continue the bubble down. 3, 2. So now let me just update this. So I have 4, 3, 1, 2. And notice that the partially sorted part has grown by 1 element. Perfect. Yes, excellent, everybody. Okay, now we do the next one. So I'm going to swap 4 with 2 here. 4, 2. So 4 is gone out of here. It grows this partially sorted part. And this element is now gone. It's gone. It's gone. Gone, everybody. So now I then do the bubble down process on this heap, which remember is only this part of the array. That's why you'll notice that last day I said bubble down only goes from the start here up to that given I minus 1. So notice I'm just going this way with my value of I. So now I have to do the bubble down. So notice I just swapped 3 and 2, because 3 is larger than 2. So I do so now I swap these two. We get 3, 2, 1 like this. And now I do this again, right? So notice I'm going to swap 3 and 1. So now 3 is right here. This grows our partially sorted part. And now I'm going to put 1 up here. And now 1's gone from here. And I have to do the bubble down, right? So don't forget I have to do the bubble down. So remember, 2 is larger than 1, and I have one child, so I automatically take that one. So I swap these two. So now I end up with 2 and 1. And then the last step is quite simple. All I do is I do the swap right here, because remember, I'm going to take effectively 2 out of this heap. And I swap them. So now 2's gone. So now 2 is gone. And now I put 1 right here. But now notice that the only element left in my heap portion of my array is 1. It's the smallest element among all of them. But now notice and look at my array. All of the partially sorted part is all over here, and I just have the smallest element sitting right over here. So this is in fact sorted. So this is how heap sort would actually sort an array, giving this heap-based implementation. Is everybody okay with that? So I just walked you through this process of how the sorting happens. So notice I don't have to do anything with this one, right? Because there's only one element left. I don't have anything I can really swap with other than itself. It's not very interesting. Okay, so that's heap sort, believe it or not. It's one of these optimal algorithms for comparison-based sorting. So remember, like we said, that there's a lower bound on comparison-based sorting of big omega n log n, and this algorithm will take big theta n log n, meaning that it optimally meets the lower bound for comparison-based sorting, because this is a comparison-based sorting algorithm. So I want to move on to another application. This one I think is kind of neat. And it really builds on something that we've actually done in the past. And I'm sure you've done this before in a previous class, but we're going to take it to its next level. We're taking it to the next level, everybody. So I'm going to consider what is called the selection problem. So there's a family problem called selection problems. And sometimes these are called k-order statistics or kth order statistics. But I'm going to consider this version of it. So I'm going to consider what we're going to call the kth largest problem. So imagine I give you an array of n comparable elements. I'm missing an S on that. Elements. And I'm also going to be given an integer k. And k is going to be between 1 and n. And my output has to be the kth largest element in the array. So I want to know what the kth largest element is in this problem. So just to give you an example of what I mean, so if I make k is equal to 1, notice that if you read the input part, it just says the array with n comparable elements, and there's an integer that's 1, and it asks for the first, that means first, the first largest element in L, which of course is the largest element in the array L. When I do k is equal to 2, I get the second largest element. 3 would be the third largest element. And if I make k is equal to n, it's the nth largest, meaning it is in fact the smallest element. So are we okay with the description of this problem? So I give you the input, there's the output, and your job is to just give me what that element's value is. So there's actually a couple really nice simple ways of solving this problem. The first one is really you just do sorting. So all you do is you sort array L from smallest to largest, then you return the position L sub n minus, you return the element L sub n minus k. And notice that the reason why that's the kth largest is that if you do a little bit of arithmetic, you think about it, if it's sorted from smallest to largest, then if I want to get the kth largest, well, the one that's sitting in the last position, well, that's position n minus 1. So that would be simply the largest. The second largest is n minus 2. N minus 3 is the third largest. So if I want the kth largest, it is n minus k as opposed to n minus 1 or n minus 2 or n minus 3. So this, of course, takes big theta n log n. That's mostly because of the sorting step. So that's a really nice simple way of solving this. Now there's another way you could do this, and I'm going to adapt this idea. So this idea is where I use a priority queue as a min heap, and I'm going to insert the n elements of my array into this heap. Now, of course, if you want to get very nitpicky about this, you could technically use heapify to build a heap that way, of course. But the point is that I'm going to perform n minus k remove min operations. So if I remove n minus k elements, so I remove all of these ones that are smaller, I should end up with the min. When I ask for the min, using the min method, what should happen? Well, it should give me the kth largest, by the very similar justification I gave for the array-based one. So I'm just removing all of these extra ones, because they're all smaller than it. So this will take n log n time, just like this one. Now, if you stare at this for a moment, you might think to yourself, hey, look, Dan, why do you really need to put all n elements into this heap? And I want to draw on just a very simple idea. So imagine I have this bag here. So I have this bag here. And I want to think about, let's just consider when k is equal to 1. I want to know the largest element. So imagine I have an array. Actually, let me move over here. First, are we okay with those two over there? These two algorithms I basically described to you. Give me a thumbs up, everybody. I just want to make sure we're all good. Don't move yet, please. Nope, that's okay. Then I'll do it. Actually, I could do it right here. So what I'm going to do is I'm going to have a series of elements. So imagine I have a bunch of elements. I apologize if these are kind of difficult to read. It's not really what the numbers are. It's more that that they are, in fact, elements. And let me move these over. So imagine I have 5 elements like these ones here. Now, I'm not sure if you can read that or not, but the point is I have 5 elements. I have 5 elements. And I want to adapt a very simple idea. So in my second approach I have over there, what I do is I simply perform with my priority queue. I just dump them all into my priority queue. Remember, think of it like a big bucket, like when I first defined priority queues for you. And you put them all in there, and then I remove all these redundant ones, right? And then what's sitting on the top of the heap is the kth largest. So imagine you have k is equal to 1. Imagine you have k is equal to 1, and I have these 5 elements right here. So one idea I have is that I'm going to take each one of my elements here, I'm going to put it into my bag if it is in fact the largest element I've seen so far. So when you do compute the largest, remember, you could just do a sequential scan left to right in the array, and you can keep track of the largest element, right? You could do that. So for example, I have these 5 here. Say I start, let me put this guy over here. Instead of putting 7 there, let's put 7 way at the end. So if I put 2, so notice I haven't looked at anything quite yet. So I have 2 right here. I'm going to put it in my bag. So now I have it in my bag here. I see a 3. Now I check in my bag and I have a 2. Now that means that this 2 is smaller than my 3. So I'm going to put my 3 in my bag. This is gone. I don't really care about it. So now, of course, I can read the 5, and I look in my bag. I look for the max element. Well, the largest element I have currently in my bag. It is, in fact, the 3. So 3 versus a 5. So if I put my 5 in here, then I currently have the largest element I've seen so far, right? And I can discard the 3. I can do the same thing with 6. 6 compared to 5, I take the 6, right? I put that in my bag. I get rid of the 5. And I have a 7 here. A 7. I have a 7 versus a 6. I take the 7, right? This should be not too ingenious, right? So this isn't too ingenious on the face of it, right? So notice that if I want to know what the first largest number is, it's what's in here. But what if I had 2? Like, say if I want the second largest? Well, I could take the same idea, Excellent. No, I'll move on over. So imagine I have the second largest. And what I'm going to do is the following instead. I have my I'm going to have my elements again, like I had before. So I have my 5 elements. And now what I'm going to do is I'm going to try to keep 2 elements around all the time. Why? Because if you think about it, if I take the smallest element out of my bag, then every element in there is going to be at least the size of whatever's in here, right? But if I have 2 of them, that means that these are going to be the 2 largest numbers I've encountered so far, right? So if I, for example, read off the 2, I put it in. I read the 3, I put it in. I put it in my bag. So now I have 2 and 3 in here. Now, as soon as I read this 5, I'm like, okay, well, what's like this might be bigger than 2 or 3, right? So what am I going to do? I'm going to take, let's see, I got a 3 or a 2. Let's take this 2 out of this bag because now I found a larger element than the 2. So now I have 2 elements that are in this bag. So it means that so far these are the 2 largest elements I have so far, where 3 is the smallest of those 2 elements. I could do this again. So I read the 6, and recall I had a 3 in here. That's a 5. Here's a 3. So I compare the 5 and the 3, and hey, look, this is way too small. So it's gone. It's gone. So I'm going to put the 6 in here. So now the smallest that I currently have in my bag is a 5. So now I read the next one. Okay, there's a 7. Well, I had the 5, right? Well, 7's bigger than 5, so it's gone. It's gone. So now, what's in my bag, though? What's in my bag? I have the 2 largest elements I have so far, a 6 and a 7. Now, wouldn't it be nice if I could know that the 6 is the smallest of all of the elements in my bag? Well, think about it. Now, imagine if this bag, inside my bag, there's this elaborate structure called a binary heap that's in this bag. So what is the smallest element in my bag then? Where is it? Where on the heap? Where is it? Is it up here? Is it somewhere down there on the heap? Or is it's at the root, right? It's right at the top. It's right at the top. So all I have to do now, if you think about it the way I just did it, I just dump the first k elements of my array into this heap. And then as I scan from left to right, the remainder of my array, I can compare the minimum of my heap. And if I see that one that's bigger, just like I did, I chuck it. It's gone. Then I put the larger one in my heap. So when I do this, notice that I can maintain k elements at all times after that point. So if I look at the top of the heap, well, what should that be? That should be the kth largest element, because there's k elements in my heap. So does everybody see that? Is that kind of neat? So all I've done is I've generalized the idea of computing the maximum using this idea that I keep a track of them in some sort of heap that's inside my bag. This is quite a magical bag. And that's all I do. So let's look at how this works then. So let me just describe what I just said right now. So let me just give you that description. Let me just erase this. Isn't that kind of neat? So instead of having to have it where you hang on to all the elements, you can actually conceptually just hang on to only k of them at all times. And if you do that, if you take a peek in your bag, right at the top should be the kth largest at that time. Okay, so below is an algorithm to compute the kth largest. So here we go. So I'm just going to start by creating an empty priority queue. Priority queue. Now remember, this is a binary heap that I'm using. So it's a binary heap that I've created. So I'm going to just insert the first k elements of L into the priority queue. So when I say that, I'm talking about L sub 0, L sub 1, L sub 2, all the way up to L sub k minus 1. So I'm just going to go through a loop, just dumping each one of these into my binary heap. And now what you're going to do is you're just going to go through the remainder of these. For each I is going to be equal to k plus 1, all the way up to n minus 1. If the key of L sub I is greater than the min, then apply remove min. Apply remove min. And after, insert L sub I into the priority queue. And then lastly, like I said, you take a peek at the top of my heap inside my magic bag. I return min. So this isn't too bad, right? Like, so you might ask, Dan, well, what did we save by doing this? Well, remember, before in my second attempt I had over on the board, I dumped all the elements into my heap, which does increase the complexity of certain operations. So I essentially took the same kind of approach, but now notice that the heap will never have more than k elements in it. Does everybody see that? It has no more than k. Just like in my example when I had k is equal to 2, there was no more than two of my numbers in that bag at any time. So let's just kind of walk through this. So I create that. That takes, this I can do in constant time, or at least depends if we talk about the array. I know how many there are, so it's n. So if I insert the first k elements into the priority queue, well, how long is these first two steps going to take in total? Well, if I'm going to insert k times into a priority queue that has heap, sorry, the heap has no more than size k, right? So I do k. Actually, let me just let's do this. Let's look at step 2 first. So it's k. So I do k insertions into the priority queue. Each time the heap is no bigger than k, meaning there's no more than k elements in it. So I know I have big theta at k log k in this case. And now this step right here, notice I go through my loop at most, well, it's roughly linear, right? Well, this third step here, well, this right here, this is, of course, big theta of, well, it's going to be roughly linear, right? So, and each time I do one of these remove min and then insertions, each one of those takes big theta of log k. Because remember, the size of the heap, the number of elements it has is no more than k. Now, if you want to get nitpicky about this step, you'd be like, oh, well, technically you create an array and it has n elements in it. So I can get away with saying, hey, look, this will take linear. Actually, I'll just write it as big O if you want to get nitpicky about this. Because remember, a binary heap can be implemented as a linked tree. So keep that in mind. So I'm just going to write big O of n, although technically if you use this as a literal tree, it can be done in constant time. And of course, this last step, since it's right at the top, I can do that in constant time. So if I add up all of these, so if I take the O there, so I have the O, and I'm just going to write that as theta n, just to make this a little easier for myself, but I'm being a little informal here. It does technically get absorbed. Actually, let me write it this way, because it does get absorbed into step 3. Like I said, the way you communicate these things, it's very careful. You have to be very careful. So that second step takes k log base 2 of k. The third step takes n log base 2 of k. And that final step takes constant time. Notice that the first step, it doesn't matter if it takes big O of n or it takes constant time, it gets dissolved into here. So this is step 1 and step 3 put together. So this gets dissolved into here. And lastly, when I put it all together, I take the most dominant of these, which of course, since k is just an integer, but n indeed cannot be no more than n, I'm just going to simply write this as n log base 2 of k. So notice that now, instead of having log n there, now it's log k. Now, first, are there any questions about what I just did here for the analysis? So remember, this first step, it depends on how you implement the binary heap. It can take constant time if it's literally a tree. It may take linear time if you're actually allocating an array of length n, where n is the number of elements you're going to put in. Because of course, actually, well, technically it's big O of k if you really wanted to get nitpicky about this, because you never need it to be more than k. So it could get dissolved here, or it could get dissolved over there. In fact, let me... Yes, what's up? Okay, excellent question. Now, believe it or not, I've never actually assumed it's a constant. I've just, in my examples, I took it as a constant. So notice that k can be a part of the input. So when I give you, say, the array, you could also give me k. So if you want to know like the third large, like say if you have a function and it has the array and then it gives you k. Well, you can provide k and it guarantees that. However, like you pointed out, and this is actually literally what I'm going to say next, so you're right ahead of the game. Notice that if k was a constant, so notice that if k is constant, how long does this take then in terms of big theta? Yeah. Okay, so notice that I have this k log k, right? And then I have n log k. Now, notice that the way I defined k, it's no more than n. So when I think about k, really, I could substitute this with n because it's always going to be bigger than it. Yeah, exactly. Yeah, no, that's exactly it. Now, if you wanted to be really nitpicky about it, you could technically write k log 2k plus this, but you'll see that, okay, well, if k is at most n, and if it's varying like that, then it just gets dissolved into this. Yeah, but you're exactly right that if it's a constant, notice that this runs in linear time, which is excellent. So if you know that you always if I only need the largest or the second largest or the third largest, for small k, this algorithm's wonderful. However, what if k was n? Say if I want the smallest. Notice that now this is going to look more like n log n, just like my second solution that I had before. So you might ask, Dan, okay, well, what do you do to make it so you can compute the kth smallest? So what if you want to compute the kth smallest instead? Does anybody have any ideas how I can compute the kth smallest using this idea? So just don't overthink it. Just think of what I described at the beginning of the lecture, how I was able to just change. Yes, somebody's pointed it out in the chat. So instead of using so in this case, I must stress that technically I'm using a min heap. So yeah, because I'm using a min heap here. So you just swap it with a max heap. Because remember, in a max heap, what you do is you keep track of you would have all these largest elements, but you always want the smallest among the k elements at all times. But yeah, so you just swap the min heap with a max heap. So you just swap the two and you get the same result. Is that kind of neat? So now if you want the k smallest, boom, there you go. Now, You might ask, Dan, is this the best way you can do this? And the answer, of course, is there's always some other way unless I can prove otherwise. Or I just lack sufficient means to prove it for you. So the answer is actually there is actually an algorithm that does run in linear time regardless of k. So if k is a constant or not. Actually, I mentioned this algorithm actually earlier on. So let me write it out. It's okay if I erase the top up here? Just want to make one remark about this. Then I want to point out one other thing that's actually very fascinating as a feature of this algorithm. Yes? Okay, so one thing that's worth noting, and this is something indeed you've pointed out, is that when you have so in our version, we defined it in terms of min heaps. So when you take a max heap, what we call min is actually, you would actually probably call it max. And instead of having remove min, you would have remove max. And they're literally independently, well, they're implemented just by flipping the inequalities that I had for my min heap. So you wouldn't have in your, yeah. Okay, so let me clarify. So if I give you, say if I have a max heap, and what I described as, say, min or remove min, so if I give you min and I told you it's a max heap, what this is actually going to behave like is if I were to write it instead as max, and remove min would be remove max. But the way I just described it to you, if I give you min, and I do the little tweaks I mentioned last day, it would actually give me the largest element as opposed to the smallest. So it's more of a technicality that's called min. Does that clarify it a little bit for you? Correct. Yeah, so yes. Yep. Correct. Yes, correct. Yeah, so notice that the big thing here is just whenever I said min before, when I talk about a max heap, you just replace it with max. So for example, when I described the remove min to you, the pseudocode for that, I would just swip around the inequalities. I may call it remove max if it makes it easier for me to see that it removes the maximum. And that's fine. But it's more of a technicality when I switch between the two. Yeah. Yeah, that's fine. That's fine. Correct. One interesting little fact, if you're doing, say, C++, is you can always overload one of the operators, and you can always change it so, like, you write your own, like, compare to method, and you override that one. So you start off with just like a heap class, then you'd have your max heap and your min heap, and you just override your compare to kind of function. So you could do that, and then the code will be essentially the same. It's just that one will have it where the inequalities are this way, and one are the other way. So you would just pick which one of them is more appropriate in each case. But yeah, no, that's a good way of thinking about it. So hopefully that clarifies what I mean. So it's just more of a technicality that I've defined the heap in terms of a min heap. If I was defining this, say, first as a max heap, I would call that max and remove max, like max and remove max if I had it right here. But yeah, it's just more of a formality at this stage. Anyways, so I want to mention one other thing, is I told you that you could do this actually in linear time. This is actually achievable there's actually a couple ways you can achieve this. So I'll say is bigger than possible. And the answer is, of course, yes. So there's a couple ways you can approach this. I mentioned this algorithm actually earlier on when we were talking about sorting a little bit. this BFPRT, medians of medians. Sorry, the median of medians. So this algorithm is, in fact, it solves that problem I described over there for arbitrary k. And it's able to do this in big O of n worst case time. It's a little tricky of an algorithm. Another way is actually there's a randomized way of doing this as well. So there's also this so-called randomized so-called, it's called quickselect. It's quite closely related to this algorithm. And if you're thinking about quicksort, when you hear quickselect, it's because the algorithms are incredibly similar to one another. So if you were to look at quickselect, if you like look at it in your spare time, it looks eerily similar to quicksort because it's based on the same idea. So this randomized part means randomized pivot, like I described that other lecture. And this runs in big O of n, worst case expected time. So the reason why I have to add this expected word, remember that if I'm adding randomization into my algorithm that changes how the algorithm operates, I actually have to compute the expected running time of the algorithm in the worst case. So when you read this, that's because I'm introducing randomization into the algorithm. So when you read that, you should just read that, hey, look, most of the time it's actually going to run like that. In fact, in this case, it's going to run like this almost all the time. It's with very high probability it's going to happen. I'm trying to remember who said this. Definitely one of the people that originally was studying these types of problems. The name is escaping me, but it said that you have a probability of your computer failing during a lightning storm. Actually, no, sorry. You have, the probability is something along the orders of your computer, you getting struck by lightning at the same time your computer fails in your house. That's how low the probability is. So it's very good. It's very good. I'm trying to remember. If I got that incorrect, I will definitely point it out next time. But that is the point is that this is a very good algorithm. It's much simpler than this one. But it just be aware that it doesn't necessarily always run in linear time on a theoretical level. But practically it almost runs linear all the time. Almost. So one other thing I wanted to point out. Yeah, the big thing, yeah. So the big thing is that you select this pivot, and that's what randomized quickselect does. It selects the pivot just like quicksort when I mentioned a randomized pivot. It does the same sort of strategy here. So yeah, they aren't independent. Yes. That's the point. Is it's really like it's but yeah. Yeah, but yeah, it's still rather. I'm pretty sure I probably misquoted him. I'll have to think about it. But I'm usually really good with this. But I apologize if I misquoted him. I'll have to think about it. But the point is that this is quite good. It's quite similar to quicksort. One other fact. I think it is just the lightning storm, or it's just simply that your computer just randomly fails. It's one or the other. I can't recall. My apologies. I'm usually really good with remembering these things. It's just sort of something I thought about just on the moment. But hopefully my point stands is that this happens in a very rare circumstance where it does not take linear time. It actually, in the very worst case, it runs quadratic. So if I just always assume that the pivot's going to be the worst one I select, it's going to run quadratic, just like what you'd expect with quicksort. But yeah, no. So the other feature I wanted to point out here is notice that in my procedure, the one I described for my algorithm, mind this is separate from that. Notice that when I go through all of my elements, notice that I really just didn't care about how many elements I was looking at. So notice that when I had my bag, I just started scanning from left to right a whole bunch of elements, right? Well, the neat thing about this is that it doesn't really matter that I know all elements in advance. So if you think about the algorithm I gave you, When I told you, oh, go through so that's step 3, the one I just erased here. When you go through those elements from k to all the way up to n minus 1, it really doesn't matter that n minus 1 was indeed the last element. This whole process still works regardless if I don't even know how many elements there are. So I just want to make one quick remark and then we're going to end things here today. At any given element read from the stream. So when I say stream, this just means that they're read from a data stream or data stream. So imagine these things are coming at you. Like say you have this program just open and it's supposed to just keep running. Say this is like an online application and you have it, so you need to make sure you compute this value as it might be coming in. So somebody might pass along a message to you and say, hey, look, here's another number. Tell me what the kth largest is out of everything you have so far. That's what I mean by a data stream. So at any given element read from the stream, the heap contains the k largest elements. It still takes big theta n log k if n is the number of read elements. And it still indeed works, exactly what you'd expect. So you just imagine I stop it, I pause this process at any time and I read those n elements. That's the running time. So this is an example of a streaming algorithm. So you can actually modify this so it actually runs so that it will work no matter how many elements I provide for it. It always maintains the k largest elements, and at the top is always going to be the kth largest. Is that kind of neat? So anyways, with that being said, next time we're going to start talking about so-called mergeable heaps. I'm going to have a few points to talk about with that. And then I'm going to be moving into our next topic, which will be involving a little bit about dictionaries. And then we'll talk about something called the splay tree after a little bit of review of binary search trees. So I'll say thank you very much and have yourself a beautiful day. I'll see you later. And I apologize again for that quote. That's definitely not something I like doing.